Okay, everything seems to work fine. We're now live on YouTube. We're being recorded. So welcome everyone. Good afternoon to the Tuesday seminars at the Warsaw University Astronomical Observatory. Today we have an honor to host Dr. Timo Prusti from ESA. Timo is the project scientist of the Gaia space mission, and Timo is going to tell us about the most recent update on the mission and the very fresh results released just last week, the early data release number 3. Timo, please.
Thanks, Lucas. So welcome everyone. Good afternoon. I will start directly with showing that what we are really proud of in this release is that we have now much more improved motions of stars through the proper motions. Before going into the early data release contents and the quality of it, let me just give a few slides of where we are with the spacecraft. Only good news, operations continue nominally. We have disturbances, so it's not that the guys at the control room are turning their thumbs doing nothing. There are always micrometeorites, microclanks, fuel movements, doing some movements on the spacecraft, but nothing which really have a significant impact on the science. In fact, it's been very quiet recent times, so we are very happy how everything behaves. As far as observations are concerned, so we don't count in millions anymore, but we go to billions. And if you go to the CCD level measurements, we are sort of already at the trillion level. And so you can imagine that the data processing task is quite demanding, not only because of the amount of data, but also the complexity of it. Just very briefly, also showing what people are people happy with the data? So some numbers from the ESA Gaia archive. So typically, we monitor how many people are using the archive, and in an average month since about 2 years, we have 5,000 users every month, and we are typically to 2.5 to 5 million queries per month. You can see in the graph at the end of the impact of the EDR3, it's only 6 days, and you see a peak forming. So I would expect that this month we will get also very high peak when the whole month is taken into account and when everyone is really starting to use the EDR3 data. It's not only that the data is being sort of exploited and used, people actually publish. So in the 2 years for the previous release, we got some 3,500 refereed papers using Gaia data. And now we see already within the few days we have had so far, a little bit more than 10, that the first papers are appearing. So some people are really incredibly quick and using the data and writing papers immediately. The contents. So we have, in comparison to the data release 2, if you look at the upper graph, the blue ones, you see that the numbers are more or less the same. This is actually totally understandable because the whole idea of Gaia is that we observe just the same stars on and on again in order to improve the parallax and proper motion measurements. So there is not like new objects coming into the catalog. It's just the same objects more or less with improved parameters. What is also flagged here is that, and I come to later that one, you see these curves which are for the various samples of extragalactic objects. So they are of course only a small fraction of the catalog, but a very important element in the sense that that provides us a possibility to look how good the quality of the astrometric solution is. And a small note of the green line, which are the radial velocities. So these are actually just the straight copy from the data release 2 with a small correction of some spurious sources which we have discovered since, so those have been eliminated from the release in EDR3. So it's slightly different in that sense, but the actual numbers are coming from data release 2. Just in numbers, I don't want to go through all the numbers. We are at 1.8 billion sources, and I mentioned the extragalactic sources. There are few of those ones. I will come back to the importance of the extragalactic sources. Maybe one comment, if you are wondering what are the 5 parameter, 6 parameter, and 2 parameter astrometry. So the 2-parameter one is where we have only solution for the right ascension and declination and cannot actually make a sensible proper motion parallax out of it. The 5 and 6 parameter ones are the most interesting ones for the community, because there we have the parallax and proper motion. The 6 parameter is actually a nuisance parameter, because the point spread function depends on the color of the object. But for some objects, we do not have good enough color. So we actually have to take as part of the solution a pseudo color, and in order to solve the interesting parameters, which are the astrometric ones. And the importance for the people using this one is that the error properties are somewhat different. So if you're really careful with error propagation and take the correlations into account, you have to be aware of this difference. Just to show in a little bit on a histogram plot that the difference of the 5, 6, and 2 parameter ones. So the 2 parameter ones are really for the very faintest ones, and really the bright stars where we only have a sort of saturated blob in the images, which are very difficult then to centroid. The 6 parameter astrometry is mostly the fainter ones and the bright ones, because there we have difficulties again due to saturation for the bright ones, and for the faint ones that the signal to noise is not good enough to have a color from Gaia. Little bit going to the performance. So in here we have plotted the parallax uncertainty note in logarithmic plot, and the improvement of with respect to the data release 2, which is the blue line, and the early data release 3 is the green line. So you see quite significant step. Just for comparison, I'm mentioning that the Gaia data release 1 which was 2 million stars, were typically of the Hipparcos uncertainty level. So the big step was made for the data release 2, and of course not only in improving the uncertainty, but also number of sources going from 2 million to more than 1 billion. And now we have a little bit more sources again, and with improved uncertainty. Clearly, for the bright stars where you have a flat performance, that's mainly dominated by understanding calibration, while for the faint stars, so from the 15 magnitudes and fainter, it's actually collecting data. So there we are not limited by our calibration knowledge. A little bit similar kind of plot for the uncertainty in the right ascension direction for proper motion. What could be noted here is that the steps from data release 2 to data release 3 are bigger. And the main reason here is that we have actually the same improvement as in parallax, understanding better the calibration issues and collecting data, but also the time span helps, of course, for proper motions. If you have longer time span, you improve in proper motion uncertainty. If you're wondering what is this peculiar blob where we have even few stars, which seem to be in the Gaia DR1 better than in the EDR3, those are in the Gaia data release 1, we gave proper motions for Hipparcos stars with the time span from Hipparcos mission. So there you also, it's a demonstration from the fact that when you are doing proper motions, if you have high accuracy measurements long time ago, you are doing pretty well in proper motions. But clearly, we will catch up, and there will be nothing better than Gaia by the next release. And just the same plot with the proper motions in the declination direction. Maybe what is more important is systematics, because the uncertainties are always the statistical uncertainties, but it's the you have to also worry about the systematics. And how do we check the systematics? Then we come to the extragalactic sources. Of course, the parallaxes should be essentially zero, as well as the proper motions. And you can see that the change with respect to data release 2, these are the same color scales. You see that the inhomogeneities in all these astrometric properties in data release 2 have been vastly improved. We have also improved the global parallax 0 point. It's still there. It's not zero. It's minus 70 microarc second. And the reason why we do not correct for this one is that for quasars, they are faint and blue. This value may be the correct one, but if your targets have a different color properties and different magnitude properties, then the 0 point might be different. There is also a paper accompanying the release which gives guidelines how to handle the parallax 0 point. Moving to the photometric contents, I would say almost if you look at the G-band is the one which the essentially white light, which we are using also for the astrometric fields. So we were already at the millimagnitude level, and now we are pushing well below millimagnitude level in the uncertainty. What is worth noting here is that what you see in the earlier releases, the wiggles, they are pretty much gone, so the calibration has improved. And what are the wiggles? The thing is, of course, that the strength of Gaia is that the dynamic range is enormous. And how do you get the enormous dynamic range? You do tricks on board. So you are using the CCDs, sometimes reading on them only partially for the very bright stars. But that again has a consequence that you have to calibrate. It's like a new instrument. And then you have to try to tie these calibrations together so that star taken in one configuration is comparable with the other one. And the earlier wiggles were consequences of the difficulties encountered with the calibration, but one can see now that with the early data release 3, all these calibration issues start to be well under control. If you want to benefit from this millimagnitude accuracy photometry, then of course, if you do precision work, you have to also know the passbands very well. So indeed, we provide the passbands and 0 points. A note here is that the passbands are slightly different with respect to the Gaia data release 2, and they will also change for data release 4 and 5. You may wonder, how on earth can a passband change? It's all related to the fact that we choose a certain quiet period from the mission, which is our reference period. And because there are always transmission loss, and there was at the beginning of the mission, there was some ice condensation on the mirrors. So depending on which is your reference period, the passbands is slightly different from another period. And now when we go further in the mission and everything is getting more quiet, we are choosing a different period, which is more quiet, because that will ensure that the photometry is even better of quality. So the price of better photometry is that the passbands will change every release slightly, not much. I mentioned already the radial velocities, that we made a small number of changes, mostly spurious ones, but also some of the objects which we could not relate, which were in the data release 2, but disappeared in the early data release 3. I will mention this one a little bit later. But essentially, it's the same set. The new radial velocities you can expect the first half of 2022, when we have the Gaia data release 3, the major part of it. Just very briefly indicating what kind of difficulties one is encountering. For example, the left plot is in the crowded fields. What Gaia is actually doing is scanning the sky, and every time what you have to figure out is that which star belongs to which star from an earlier scan. And of course, if you have stars with proper motion or in crowded fields, this can be quite a complicated effect. So in the earlier releases, we tried to do, of course, the best we could. And now when the astrometric accuracy is improving, it's easier to assign sources to individual sources, even in crowded fields. So if I quickly flicker, you can see, for example, at the upper left corner, something what we thought was one source connected with the green lines. Now in EDR3, it is split into 4 different sources. And this is also the reason why not all sources in data release 2 are existing in early data release 3, because we have found all these kind of erroneous cases and corrected them. The same is visible at the right-hand side. It's quite difficult actually to detect the high proper motion stars, but now the algorithms are much better, so we recover much more the high proper motion stars in the early data release 3. In order to cope a little bit of this fact that sources are changing, we provide a neighborhood table to relate sources to the data release 2 sources. Reference epoch has changed to 2016 because we always try to put the reference epoch in the middle of the period, observation period, because that's where we again get the highest accuracy. I mentioned already the passband and 0 point changes and the completeness in crowded regions, the improvement. We have also now lowered the limit how close to what we consider two different sources can be. It used to be 0.4 arcsecond, so now we dare to drop this to 0.18 arcsecond. So sources which are at this distance and seem to be different ones, we also leave them in the catalog. So a little bit of a summary. If you go to the archive, you have to sort of figure out the main table, but okay, you don't have to remember this by heart. It's quite visible there. It's the Gaia source table where all these entries are listed. And we have the match table from the data release 2 neighborhood. We have various tables listing the extragalactic sources. We have also simulations available. So if you want to examine whether your selection is compatible with your science case, you can use these simulations to look what is expected. People who are interested in selection function, we have the scan law available and also the biggest gaps which we have had during the observing runs. And then we provide pre-computed cross matches. Like we had in data release 2, of course, we always encounter things, we learn errors in the release, and we try to collect and keep up to date a list in known issues page. So you can, if you start to use data, it's always good to also check that there is nothing new in this area. Obviously, there is extensive documentation available, and also we have a help desk. So in case you have questions, you don't understand something, you can always drop a mail to the help desk. But in addition, really the details are described in a set of calibration and processing related papers, which the titles are at the upper part of this page. And those are really the ones to consult if you want to really understand in detail what is happening and how the data has been calibrated and what possible problems might be there. Many of the issues which do exist have been described and a reason why they exist and how to deal with it. In addition, we started already earlier a concept of performance verification papers. So these are really a chosen scientific topics where we have a group within the Data Processing and Analysis Consortium using the data for a specific scientific problem. And the idea is not to exhaust that topic, but just demonstrate how much further you can go given the improvement in data quality. So this time for the early data release 3, we had 4 papers. So one is the catalog of nearby stars. One is a study of Magellanic Clouds. Then there is a study about the Galactic Anticentre. And finally, there is about the acceleration of the solar system from Gaia astrometry. So I will briefly just mention a few things of all these papers. So if you look at the Gaia catalog of nearby stars, so of course, if you go to something like 10 parsec sample, that was pretty well known already from Hipparcos and especially from the ground. But as your horizon, if you put horizon further and further, more and more incompleteness in our knowledge exists. And like the graph below shows that 100 parsec sample, almost all stars are now discovered by Gaia. You can imagine that if you are studying the nearby stars, there are many issues what you can deal with. So rather than trying to explain all these issues what have been addressed in this paper, I just glanced through very quickly the topics so that you have an idea what kind of topics you can find from this paper, so that if that topic interests you, you can actually then go to this paper and consult that part of it. So for example, there are studies about the position of our sun with respect to the galactic plane and how different spectral type stars relate, what are the average heights of those samples. Luminosity function is, of course, one fundamental step if you want to understand the mass function in the solar neighborhood, and if you're interested in topics of initial mass function. One can get the local kinematics because the radial velocities exist for the nearby stars, the sample of 7 million from the data release 2, and then you can plot things in the UV plane and see the concentrations which have been already discovered in data release 2, but now, of course, with the better proper motions, the quantities are better determined. The number of ultra-cooled dwarfs has increased, even though Gaia is obviously not the optimum wavelength coverage for these ones. One would be better off in the infrared, but still the sensitivity is enough that there are new stars found in the 100 parsec sample. Clusters, there are a couple of known clusters within the 100 parsec, so Hyades and Coma Berenice. And I think with the clusters, really the Gaia strength comes at full glory, because something like Hyades, we think is as a compact cluster, but the reality, if you take the tidal tails into account, the Hyades stars are all over the sky, and it's only with the Gaia kinematic information when you can find the stars which actually belong to the Hyades. So if you're interested in cluster studies and these aspects, you can also study this paper. Of course, binaries, if you are resolving binaries, but even if you are not resolving binaries, the best statistics you can achieve from a close-by sample, so the 100 parsec sample addresses these issues. And finally, there are also lots of white dwarfs in 100 parsec sample. And of course, the white dwarfs, that was one of the beautiful moments of the data release 2, where we had these different sequences in the white dwarf evolution. And what I think is one of the nicest things, you see this concentration, which is going sideways of the sequence, which is the crystallization of the cause of white dwarfs, which was 50-year-old theoretical prediction, which was beautifully really shown with the Gaia data. So let me move to a couple of slides of showing what was discovered in the study of the Magellanic Clouds. So the idea was to study the structure and kinematics of Magellanic Clouds, and the reason why this was chosen is that it is actually very challenging. The distance is, of course, very large to the Magellanic Clouds. So it's like showing what can you do at the limit of Gaia astrometry. And also, there is a large section which I don't go into here, is that various astrometric problems which you can find in the Gaia data, they are very visible in the Magellanic Clouds studies, and that has been addressed in this paper so that users can sort of get guidance that what you have to watch out if you're really working at the limit of Gaia performance. One of the early results from data release 2 was already the clear indication of rotation of the large Magellanic Cloud, what you see in this artistic lick type image. And then small Magellanic Cloud, the structure is more chaotic. And now with the early data release 3, all this phenomena is much more visible in the data and can be studied. There is also, with the Gaia data, was already studies of the bridge between the Magellanic Clouds, which was, of course, also previously known from gas. And now the nicest part, I think, was study of the looking especially the young stars. And one could see that there is a streaming of the small Magellanic Cloud towards the large Magellanic Cloud. And how they made this in this paper visible is that they took only the blue stars, the young stars, and then they started to enhance the populations more and more, that you can really see the very fainter stars. And if you look right in the middle of Magellanic Clouds with large and small Magellanic Clouds, and start to look how the proper motions behave, so you can actually see the streaming motions of the stars in this bridge going from a small Magellanic Cloud towards the large Magellanic Cloud. Now, the third paper which I will address is the Galactic Anticentre paper. So just to put us in perspective, so we are, of course, 8 kiloparsec roughly from the galactic center. So if we say that, okay, our horizon is 8 kiloparsec, so if you look then to the other direction, then we are actually looking 16 kiloparsecs away from the galactic center. So there is an advantage to look at the galactic anticentre direction, because we can probe areas which are very far away from the center. So it is also the place where we expect to see different kind of structures than in the solar neighborhood. So there are still remnants of the ancient and disrupted stellar systems which come from outside the Milky Way. And we should also see all kind of signatures of perturbations encountered by our Milky Way. And I think the numbers, what was analyzed here, 21 million sources, it's a sort of indication of the point of having a Gaia sample of more than 1 billion stars. When you observe more than 1 billion stars, so then if you choose a specific topic to study, you still are working with reasonable samples to do statistical analysis. That, I think, is one of the strengths of Gaia, that you can always have a reasonable sample to do proper analysis. Now, just listing the advantages of anticentre is that, of course, it's a direction where the extinction is lower. And the important thing is that because we don't have radial velocities to really distant faint stars, but it doesn't matter so much in the anticentre direction, because with the proper motion, you already get the rotation and vertical velocities by astrometry. And it is exactly the proper motions which are really good in the early data release 3. So the early data release 3, more stars, better uncertainties, and further reach. Now, just a little bit introduction of to a couple of things what is coming. You may recall that one of the data release 2 discoveries was that something called Gaia Enceladus, a small galaxy, has merged with the Milky Way some 10 billion years ago. And the remnants of this merger can be seen in 2 ways. So first of all, we can see the stars which are from this other galaxy. We can distinguish them kinematically, but we can also see in the thick disk, which was heated by this merging event, the old stars. So they were in the original Milky Way disk before this 10 million year time, but they got heated into the thick disk. So if we separate these 2 populations and look what happens to them in the galactic anticentre direction, so one can look how the blue and red sequence, when you are close to the sun, they are both existing there. When you go to a little bit further distances, you start to see that the red sequence is disappearing. And when you look really far away, the outer disk, the red sequence is almost gone. So in this paper, they could conclude that the thick disk sequence, it sort of stops at 14 kiloparsec, while the blue sequence, which was a sort of intruder to our Milky Way galaxy, extends much further away. I didn't go through all the items in this paper, so there are lots of studies of these patterns of movement in the outskirts of the galactic disk, and density structures, and also orbits of open clusters. I only mentioned this size of the protogalactic disk and the remnants of this past merger, which can be seen in the anti-center direction. Okay, let me move to the next topic. So this is the galactic orbit of the Sun and solar system. Again, just a reminder what is happening. So we are, of course, at 8 kiloparsec from the galactic center. We are going with the speed of the order of 200 kilometers per second around the galactic center. Of course, we are also having additional movement, like bouncing up and down in the vertical direction. And this sort of one revolution around the galactic center takes about 220 million years. When we are doing the Gaia astrometry, the astrometry is with respect to the solar system barycenter. So that means, of course, that we are measuring everything in an accelerating reference frame. If we say that the quasars, for example, which are really at far distances, form reference frame which is rigid, because we are in a system which is accelerating, we expect to see proper motions in quasars, which is due to the solar motion rather than the motion of the quasars. So if we simulate that one and put just quasars on the sky and see what we should see a pattern where the quasar proper motions, depending on the location of the sky, they all seem to be going towards the galactic center. Of course, I mean, this is very small motion, and the predicted motion is at the maximum at the level of 5 microarcsecond per year. Now, you probably cannot remember anymore when I showed the proper motion accuracy plots earlier. They were typically for the magnitude range where quasars are, they are several tens of microarcsecond per year. So this means that we can never measure this effect from a single quasar. The only way to measure this one is to look all the quasars at the same time. And then you are trying to look whether you see this pattern as expected. So the pattern, what is expected is that the proper motions of the quasars are going towards the galactic center. They're at the maximum at 90 degrees away from the galactic center, and they are going away from the galactic anticentre. And the effect is really extremely small. We are talking about a fraction of nanometers per second square. So it corresponds to this, what I mentioned, at maximum the 5 microarcsecond per year of proper motion. And typically, we would expect proper motion of the quasars at 4 microarcsecond level. All of them totally not possible to measure on a single object. The effect is, of course, really, really small, and there are very good estimates what kind of values to expect. And there is the axisymmetric part, which is the majority, but it is good to also notice that our galaxy is, of course, not axisymmetric, but we have inner bar, we have spiral arms, we have molecular clouds, and we also, the sun is not exactly in the galactic plane. So this galactic asymmetry is also cause acceleration, which is not towards the galactic center. Also, the Large Magellanic Cloud is pulling us, other local group galaxies, but individual stars nearby, they actually don't matter in this game at all. I don't want to look all these numbers. I just say, what did we get for this maximum when fitted to all the quasars what we're seeing? We get 5 microarcsecond per year, so pretty close to what is predicted, which is sort of a good thing to give trust. And if one looks at the acceleration parameter, we are talking about accuracies of 16 picometers per second squared of the in the acceleration. And if you look then, where are we accelerating? So we are accelerating pretty close to the galactic center, as we should. The fact that it's not perfect is understandable because of the other effects. So we are not accelerating perfect towards the galactic center because of the other impact. What is sort of peculiar here is the Gaia point, blue one, and there's a VLBI measurement where we are accelerating. So there's clearly a discrepancy. So I'm sure this topic has not yet been exhausted, and there is much to be seen. We were a little bit afraid to make this result public because we were afraid what will the press say when we tell that we are accelerating towards the galactic center. And of course, we were not disappointed. This is what sensational newspapers make out of this kind of scientific results. Apparently, I didn't read the article. I only got this shocking front page news. But actually, apart from the title, apparently the story was actually quite correct. Just a sort of semi-philosophical remark is that with Gaia, we cannot determine the velocity of our solar system, but we can get the acceleration. But the velocity can be done, for example, the Planck mission, when you have looked at the intensity, the dipole of the cosmic microwave background. So with combining two missions, Gaia and Planck, we can actually tell where our solar system is heading towards and how it is accelerating, which is sort of quite a funny side comment. Just very briefly, a couple of very quick papers which appeared from just community after the data became public. This one is quite nice by John Bowie. What he did, he said, fine, now we have a measurement of the absolute acceleration of the solar system. From pulsars, from binary pulsars, we can get the relative acceleration with respect to the sun. If we take the Gaia as a truth of the sun acceleration, we can actually address the question of rotation curve. Well, it all fits. The black point is the one which is set that's the absolute given by Gaia, and the blue points are done when you are using this value in the reduction of the relative acceleration of the pulsars, and then you can see how the pulsars are compatible with a flat rotation curve. Actually, what they used here, the red curve, is very quick, very close to what was known already earlier. But it's a very neat idea that you can directly apply a Gaia result into a wider context. Another quick paper was, again, somebody who was very well prepared and had queries ready, was looking at the high velocity stars. So which are the stars which are candidates that they are not bound to the Milky Way, but they are they can be either moving away or moving inwards, in which case they are of extragalactic origin. But you see the error bars are quite large, so I think here is still further work needed, but also a nice demonstration how data can be used quickly. Now we are already more than 10 papers are using early data release 3, so I'm getting the luxury problem that I cannot keep up to speed that what kind of results are coming, but these were 2 very quick ones which came out by the community. Let me very briefly mention that what is happening the second half, the first half of 2022, when we are making the data release 3, so the remaining part of it. So first the astrometry and photometry. So it will be the same 1.8 billion stars as in this early release, because we are not updating the astrometry and photometry. What will be new is about 30 million radial velocities. So that goes from 7 to 30 million. So you can imagine that for Milky Way studies of kinematics, that will be a significant step. We expect some more than 7 million variable stars with classification and characterization and light curves, and astrophysical parameters to some 300 million sources. We are also going to give mean spectra, but we still have to look which are precisely the numbers which we can validate sufficiently. For solar system, we expect some 100,000 solar system objects with the epoch astrometry, including orbit solutions, and also reflectance spectra for some 5,000. We will also provide the first solutions of double stars, but here the tests are still ongoing, so we have to see how many are reliable that we can actually put out to the community. There will be also more detailed properties of extragalactic sources. And one thing what we want to provide is we took the Andromeda galaxy and just a 5.5 degree radius and give all the photometry of all sources, variable, non-variable, so that people can get used to what will be provided and in later data releases. Just one more thing which I think is worth noting in the data release 3 is the spectrophotometry. So in the left-hand side, you see the sort of spectral energy distributions of objects with different colors. So you can sort of roughly say that the blue ones would be hot stars and the red ones would be cool stars. So in the cool stars, you do see the molecular bands, and you see that easily that spectral type and temperature, effective temperatures can be deduced from this data. But here is an image where a little bit further study was done looking at the details of this spectra. And actually, if you do a statistical analysis using them, you actually even these data, even though it looks like it's not very high resolution, one can deduce the metallicities and even alpha elements of this spectral energy distribution. So making this tens of millions of these spectra available for the community will allow a lot of science to be done by the community. Let me start to wrap up a little bit and go to see a little bit look in the future. Well, we have completed this, what we call the Gaia nominal 5-year mission that we completed summer 2019. So we are now in something called extended phase. What is the real end of Gaia? We expect somewhere February, May 2025. And what will be the end of Gaia? It will be run out of consumables, and specifically for the micro-propulsion system, which we need to keep the scan speed controlled so that it's good enough for astrometry. So when that consumable runs out, we cannot scan precisely enough to do proper astrometry. So that's then truly the end of the mission. But if spacecraft for the rest continues to work till the end of this consumable, then we will have more than 10 years of Gaia data available, and I think that that will be a fantastic legacy for decades to come. There is, of course, a formal part when we go outside of the nominal 5-year mission. So it's an ESA system how missions extensions are approved. And at the moment, we have approval till the end of 2022. And already an indicative approval, which has to be confirmed till the end of operations. I'm pretty confident that the Gaia track record is good enough that I'm not worried that this indicative would not be turned into a permanent one, so that we can actually use the satellite till the end of its operational lifetime. Just going a little bit back for the first seconds of when the archive was opened, I do see also in Poland some stars, but some users very early on. But it went within seconds to several hundred users, and I think the accesses went above 10,000. So maybe the most early users were having Python scripts ready and making the queries directly as it became available. So it was quite impressive, and luckily no technical problems. So I think everyone was served, and archive didn't collapse because of the usage. And I just conclude by showing this little bit advertisement, the numbers of what is in the early data release 3, and well, I leave you to read it, and I stop here and take questions. Thank you.
Okay, excellent. Thank you, Timo. I'll do the clapping on behalf of everyone. So we have time for questions, and if you have a question, then please raise your blue hand in the participants menu. And I already see Radek Poleski. Please show your face and ask your question.
Hi, thank you very much for a nice talk. The question I have is about the distance to the galactic center. Do we have a new measurement of that distance from the Gaia after early EDR3?
Not really directly from Gaia, because so we are essentially observing an optical wavelengths. So we do miss the close by galactic center objects. So it will be always an indirect measurement, which is, for example, this Bowie paper, which I mentioned. They do a kinematic determination of the distance. So you can deduce the galactic parameters based on Gaia data, but not directly.
Okay. Yes, question from Alex, please.
Hi. Is there an archive from which one can download calibrated photometric light curves for any given arbitrary RAN deck and covering the entire mission timeline? Specifically, our group is interested in AGN. We see that for Gaia alerts, there's the photometric science alerts website, which has light curves for science alert targets. But if we're interested in other non-alert targets, is there some online tool that's already available?
Not yet. So this is we have the so the alerts are there. So okay, you are aware of that one. Then we have from the data release 2 variable stars and light curves, which were analyzed there. So that's maybe rather limited. And currently, the processing for the photometry is being processed by the variability processing unit. And this will be part of the data release 3 proper. And the expectation is that there will be more than 7 million light curves. Specifically, the AGNs, there is a specific group also looking the AGN light curves. And this is in the planning to get published. But I had the caveat in the slides that we still want to verify everything before making sure that everything can be published, because we don't want to get unvalidated data available. So you need patience till first half of 22.
Thank you.
Well, I have a question as well. You mentioned that in EDR3, the closest separation between resolved sources is significantly smaller than in DR2, changing from 400 milliarc seconds to 180 milliarc seconds. So how reliable, if I find two sources separated by this distance, how reliable are the measurements of proper motion and parallax of these two? Or do you see they are correlated very often, or are they really separate sources in Gaia?
So this was a study made. I think we were a little bit too conservative in the data release 2. So there was a study then made that where do we think that sources can be reliably, that it's not some sort of fluke of the processing, and we came to this 180 milliarc second distance. Of course, if you can always go to an individual star and there might be an error, but the bulk of stars which are this separated, they are seen as a separate objects and they should be reliable.
Great, this is perfect. Right, I don't see questions on YouTube neither, nor here. So thank you, Timo. Thank you for this very interesting and enlightening talk. And we'll continue on Gaia EDR3 actually next week. Laurent Ayer from Geneva will tell us more about his area of Gaia involvement. So I invite you, all of you, to join us next week to find out more about Gaia EDR3. And now I thank you all for joining. Thank you, Timo, again, and goodbye.
Thank you. Bye-bye.